Good afternoon, class. We are looking at Chapter 2, Limits, Section 2.3, Limits of Functions at Finite Numbers. We've looked at limits of sequences, limits of functions at infinity, and now limits of functions at finite numbers. Recall, limits of sequence, here's the summary. A sequence is an ordered list of numbers or function f whose domain is the set of natural numbers 1, 2, 3 to infinity. Limit refers to the long-term behavior of a sequence, i.e. what happens to a sub n of a sequence in a long run. The limit of a sub n as n approaches infinity is L. We say that a sub n converges to L. Limit of a sub n as n approaches infinity is infinity, negative infinity, or does not exist. We say the sequence diverges. To find limits, simply plug in the value and observe. Some of the theorems. Limit of 1 over n to the power of p as n approaches infinity is 0 for p larger than 0. The limit of r to the power of n as n approaches infinity depends on the value of the base r. If it's between -1 and 1, the answer is 0. If it's 1, is 1. And if r is larger than 1, the answer is infinity. For example, when we look at a given geometric sequence and we add them up, which becomes a geometric series, S sub n is summation of a r to the power of n minus 1 from 1 to n equals a plus ar all the way to the n and to the end, and it's a times 1 minus r to the power of n over 1 minus r. If r is between -1 and 1, then the limit of S sub n as n approaches infinity is the limit of this expression, a times 1 minus r to the power of n over 1 minus r. So when r goes from -1 to 1, this r to the power of n, its limit goes to 0. We get a over 1 minus r. A geometric sequence can be solved. B sub n plus 1 is r b sub n using recursive format, or b sub n equals b sub 0 r to the power of n, bear in mind, or b sub 0 is the same as a. This is explicitly. If we add a constant to this, like when we give medications to patients at a specific time step, then we get to b sub n being b sub 0 r to the power of n, plus we add this term c times 1 minus r to the power of n over 1 minus r, as usual, b sub 0 or. Finally, reminding everybody of the horizontal asymptotes. A horizontal asymptote of a curve y equals f of x is y equals L if the limit of f of x as x approaches negative infinity is L, or the limit of f of x as x approaches infinity is L. So this is the synopsis of what we've covered. And now 2.3, limits of functions at finite numbers. Finding limits by numerical and graphical method. Definition, limit of f of x as x approaches equals L. Here's how we read it. The limit of f of x as x approaches a equals L. So let's look at all these three graphs. We are interested in the limit of f of x as x approaches a. In all three cases, the limit equals L. Take a look. When we say a along the x-axis, from the left, we go this way. From the right, we go this way. Both of them are approaching this point. From the bottom, from the top, and in all cases, the answer is L. Same thing for here and here. But what's the difference among those? In part A, f of a is also equal to L. There is no discontinuity. F of a represents the functional value at precisely x equals. In part B, f of A, you look at the solid point is B, which is not equal to L, makes it discontinuous at x equals A. Finally, in part C, f of A, we don't have any solid points. It's not given. It's undefined. But nevertheless, okay, but in each case, regardless of what happens to A, the limit of f of x as x approaches A exists and it's equal to A. One-sided limits. A function has a limit at A if the limit of f of x as x approaches A from the left equals L, and limit of f of x as x approaches A from the right equals L. Therefore, the limit of f of x as x approaches A equals L. This is read A from the left. This is read A from the right. And VA short for vertical asymptote. The limit of f of x as x approaches A from A or A from the left or A from the right is positive or negative infinity, gives rise to the equation of x equals A being a vertical asymptote. This is the synopsis of the entire section. Example 1, finding limits by numerical and graphical method. Guess the value of the limit of x minus 1 over x squared minus 1 as x approaches 1. Well, first thing first, we call this f of x. F of x is x minus 1 over x squared minus 1 is not defined when x equals 1 because the denominator becomes 0. Does it matter? The answer is no, because we don't care what happens at 1. We want the limit as x approaches 1. We never get to 1. So having said that, we are going to look at it from different methodologies. Number one, we're going to start with the numerical method. Numerical method. Let's evaluate the function f of x equals x minus 1 over x squared minus 1 with so many decimals for values of x that approach 1 but are not equal to 1. So that means either from the left or from the right. So the tables below give values of f of x for values of x less than 1 and larger than. So for x less than 1, for example, 0.5, 0.6, 0.7, 0.8, even 0.9 is way off. So we add more nines after the decimal. We evaluate the function and we make a note of it. So that's from the left. Now from the right, for x larger than 1, for example, 1.5, 1.4, 1.3, 1.2, even 1.1 is way off. So you add some zeros between these two ones after the decimal. As you add more zeros in between, you get closer and closer to 1. You put it into this, you evaluate it, you look at the last row. So this number gives us this one, this number gives us this one, and I hope you see from both sides clearly the table indicates the limit of x minus 1 over x squared minus 1 as x approaches 1 equals 0.5 or 1/2. 0.5 or 1/2. Now, let's look at it from a graphical point of view. I hope you remember when you want to graph a rational function, the very first step is to put it in lowest term. So if there is a common factor between the top and the bottom, you drop it. And if there is a common factor, where the common factor happens at the x coordinate of that, you get a whole. And that's exactly what happens here because there's a common factor of x minus 1. However, as we approaches 1 from the left and right, from the left, from the right, or along the x-axis from the left in the as far as the curve is concerned and the right, they both take us to 0.5. So numerical method gives us 1/2 or 0.5. Graphical method gives us 0.5 or 1/2. But more importantly, you should be able to do it algebraically or analytically. And that's what I expect you to do it for your exam. Unless there's a specific question that asks you for a numerical method or a graphical method. So methodology is this. If you plug in, you get 0 over 0. The technique is to factor. To factor, notice the denominator is x squared minus 1 or x squared minus 1 squared. So a squared minus b squared is a minus b times a plus b. This becomes x minus 1, x plus 1. You drop the common factor, and the numerator becomes 1 and over x plus 1. If I plug in 1, I get 1/2, which is identical to what we got. Again, this is the method you're supposed to do it, algebraic method to prove that the answer is 1/2. One-sided limit. The function h is defined by h of t equals 0 when t is less than 0, 1 when t is larger than or equal to 0. This is a piecewise defined function. The limit of h of t as t approaches 0 from the right equals 1 because you look at the greater than. So the symbol x approaching a from the right, this plus means a from the right, means that we consider only x larger than a. Limit of f of x as x approaches a from the right. The symbol x approaching a from the left means that we consider only x less than a. Limit of f of x as x approaches a from the left. And so limit of h of t as t approaches 0 from the left is 0 because you use the less than. The limit of h of t at t approaches 0 does not exist because there are different values. Also, note that h of 0, you look at the equality, it is 1. If we were to graph it, this is y equals 0, the x-axis, or in this case, the t-axis, but for t less than 0, so you have a hole here, this portion. And y equals 1 is a horizontal line, but starts from 0, and it's a solid point because of the equality. So you can see the graph, and of course, the one-sided limit indicates a function has a limit at a if the one-sided limits are identical. The limit of f of x as x approaches a from the left and right must be the same for the limit to exist. Okay. Let's look at this graph. And example 2 says, given the graph of a function g, state the value if they exist of the following. We are interested in finding the limit of g of x as x approaches 2. Therefore, we are going to go to one-sided limits. So number 2, along the x-axis, find it. On the left side, we are approaching 2 from the left, puts us in this branch. We are moving towards this hole. The answer is 3. Please understand, we are looking at the limit. We never get to that point, okay? Doesn't matter, it's a hole or a solid. Now, going back to number 2, limit of g of x as x approaches 2. Now, this time from the right side of 2 puts us in this branch. And this hole, we are moving towards this hole with the y coordinate 1. Are these two the same? No. Therefore, the limit of g of x as x approaches 2 does not exist. We're going to look at the limit of g of x as x approaches 5. And again, we're going to do one-sided limit. Now, locate number 5 on the x-axis. The left and the right side both will put us in this portion of the graph from the left, from the right. So from the left, and from the right, both of them will take us towards this hole, which has a y coordinate 2. So the limit of g of x as x approaches 5 from the left is 2, and the limit of g of x as x approaches 5 from the right is 2. Because the two are identical, the limit of g of x as x approaches 5 does exist, and it equals 2. However, what I want you to notice, at 5, we have this point, solid point, which has a y coordinate almost 1.4, that is g of 5. So g of 5 is equal to 1.4, which is not equal to the limit. Whereas g of 2 is just missing in action. We don't have it. We don't have any solid point. It's undefined. By the way, both these points, and we'll discuss it further later on. At 2, it's discontinuous. At 5, is discontinuous. The difference is the 2 is a jump. There is nothing you can do to fix it. But this one is removable, and therefore we can fix it. We'll discuss that later on. We are going to look at another graph, and we are interested in finding the limit of f of x as x approaches 2. That's why we're going to look at one-sided limits again. So we locate number 2 along the x-axis and approaching it from the left, limit of f of x as x approaches 2 from the left this way. We are moving this way, which puts us in this branch having a y coordinate equal 3. That is the limit. Now, for this one, we locate number 2. We are approaching it from the right, and it puts us in this branch, moving towards this hole. The y coordinate is 1. Therefore, the limit of f of x as x approaches 2 from the right is 1. Because these two are different, the limit of f of x as x approaches 2 does not exist. We want to look at a few more things, starting with f of 2. You look for a solid point. There is a solid point, which has a y coordinate 3, and we write f of 2 equals 3. Again, later on, when it comes to continuity, please understand the function is discontinuous at 2. Also, you see that it's discontinuous at 4. But for now, because there is a solid point here, and these two, limit of f of x as x approaches 2 from the left and f of 2 are the same, we say it's continuous. The function is continuous at 2 from the left. Needless to say, it doesn't change the fact that it's discontinuous at 2. What about 4? Locate the 4 along the x-axis. The left side moving this way, the right side moving that way. Both of them are moving towards this hole, which has y coordinate equal to 4. Therefore, the limit of f of x exists as x approaches 4, and it's equal to 4. Now, what is f of 4? We look for a solid point. It doesn't exist. It's undefined. But the difference again is this is a jump, and we can't fix this discontinuity. But this is called a removable discontinuity. All you have to do, define f of 4 to be equal to the limit, and then it becomes continuous. This definition is illustrated graphically in the following figures. What definition? Infinite limits. If you look at both cases, in this case, the limit of f of x as x approaches a from the left and right, both of them take us to infinity. On the other hand, this one, limit of f of x as x approaches a, both sides go to negative infinity. Similar definitions can be given for the one-sided infinite limits. All of these are one-sided. For example, this one, the limit of f of x as x approaches a from the left is positive infinity, and this one from the right is positive infinity. This one, the limit of f of x as x approaches a from the left is negative infinity, and this one from the right is negative infinity. And that gives rise to the definition of a VA. The limit of f of x as x approaches either a or a from the left or a from the right. If it's positive or negative infinity, either one of them gives rise to vertical asymptote having equations x equals a. So that's pretty straightforward, everybody. As an example, again, this is the definition. As an example, if you look at y equals ln x, recall logarithmic functions, when the base is larger than 1, they all look similar to that. They uh, have the x-intercept of 1, 0. They have a domain from 0 to infinity. They have the range, all real numbers, and they have a vertical asymptote. As you can see, this goes to negative infinity. So the limit of ln x as x approaches 0 from the right is negative infinity. That means x equals 0 must be the VA, vertical asymptote, for the function y equals ln x. The graph is given, and we want to find the limit of r of x as x approaches 2 and other numbers. And again, reminding you of the definition of a VA. So having said that, let's look at number 2. Find and locate number 2 along the x-axis. From both sides, it's going down to negative infinity. So the limit of r of x as x approaches 2 is negative infinity. The limit of r of x as x approaches 5, locate 5. Both sides of 5 will result in infinity. So limit of r of x as x approaches 5 is infinity. However, as we approach negative 3, limit of r of x as x approaches negative 3 from the left goes down to negative infinity. Limit of r of x as x approaches negative 3 from the right, positive infinity. So according to definition of a VA, if you look at this one, that means x equals 2. If we look at this one, that means x equals 5. If we look at this one, that means x equals minus 3, and that gives the same result. These two, both of them, give the same result. And so x equals 2, 5, and x equals negative 3 are VAs, vertical asymptotes, and we write the equation next. The limit of square root of x plus 4 minus 2 over x as x approaches 0. And we are going to look at the solution by algebraic method class. Okay. The very first step is to plug in. Notice if I put 0 here, I get 4. Square root of that is 2. 2 minus 2 is 0. This is 0. 0 over 0 is an example of a case which is indeterminate. And as you recall, indeterminate in short means more work, meaning use your algebraic techniques. So what is the algebraic technique that we are going to use? Whenever you have a square root involved and you plug in, you get 0 over 0, you have to multiply and divide by its conjugate. So because it's 0 over 0, you're going to multiply and divide by its conjugate. First of all, the reason we multiply and divide because this is 1, and that's okay to multiply by 1, number 1. Number 2, how do you move on? When you have 0 over 0, it is the 0 in the denominator that creates a problem. So the denominator, you keep it as a product because you're hoping to get rid of x. You never, ever distribute. So you distribute the top. Recall a minus b times a plus b is a squared minus b squared. So this would become square root of x plus 4 quantity squared minus 2 squared. And I want to remind you, minus 2 quantity squared is 4, but minus 2 squared is minus 4, and it has got to do with the order of operations. Don't mix them up. Okay, and so x plus 4, square root of x plus 4 quantity squared comes out, becomes x plus 4 with minus 4. 4 and minus 4 cancel each other. These two cancel each other. We get 1 in the numerator. And now if you plug in, you get the square root of 4, which is 2, plus 2 is 4. So 1 over 4 is the final answer. So 0 over 0, it's an indeterminate form. Anything can go. So you use your algebraic techniques to figure out what the answer is. Looking at both of these questions at the same time, the limit of x plus 2 over x plus 3, in this case, as x approaches negative 3 from the right, as this case, as x approaches negative 3 from the left. First and foremost, I want you to know, for the numerator, it doesn't matter from the left or right. The answer is negative 1. For the bottom makes a difference. So for now, I'm going to put minus 1 over 0. If you just look at minus 3, never mind from the right or left. Minus 3 plus 2 is negative 1. Minus 3 plus 3 is 0. Same thing here. Minus 3 plus 2 is negative 1. And this one is 0. But what is the difference? And that's what I want you to pay attention to. I want to show you how you arrive at the answer, because when you divide by 0, the answer is no longer undefined. You have to go with negative or positive infinity. Which one and why? Okay. Now, if you have a number that is positive, for example, if I go with number 3, okay, the left side is like 2.9 and the right side is 3.1. Both are positive. This is positive, so is this one. If I go with a negative number, for example, negative 3, the left side is like negative 3.1. The right side is like negative 2, negative 2 point, let's say 9. And again, both of them are negative, everybody. Okay. 0 is the only number, the right side is positive, the left side is negative, and that's is important. That makes a huge difference, because what you divide by a negative number or positive, that's important. So for that, if you look at this example, negative 3 from the right, okay, like negative 2, you can even go with negative 2, but because we want the sign. But negative 2.9 plus 3 is positive 0.1. So it's negative 1 over 0 from the right. Whereas here, negative 3 from the left, like negative 4 or negative 3. You can even go with negative 4 large, because we want the sign. Plus 3 makes it negative 0.1. Is negative 1 over 0 from the left, which means we know both of them are infinity, but this one negative over positive, negative infinity, negative over negative, this one is positive infinity. That's how you figure out positive or negative infinity. Let's look at this example. Again, 5 is approaching from the left. For the numerator class, makes no difference, is e to the power of 5. Now e to the power of 4.999, or even from the right, 5.11 makes no difference, is e to the power of 5. This one, it's 0 to the 3 power. Now this 0 is important to know whether it's from the left or right. The top doesn't make any difference. Again, 5 from the left, like 4.9. E to the power of 4.9999 or e to the power of 5. It's a positive number. But from the left, what happens to the denominator? So we are interested in looking at this part. So 5 from the left, example of that would be 4.9. You can even go with 4, because we want the sign is negative -0.1 or just even -1. You just want the sign. Therefore, you're looking at this one being 0 from the left. Of course, I'm keeping the exponent. Now, recall when you have a negative number, for example, -3, okay? If I square it, I get +9, but if I cube it, I get -27, meaning this one has an even exponent. This one, it has an odd exponent. And because this is an odd exponent, 3 is odd. Any odd that remains as negative, and so therefore the answer is -infinity. So I hope you see how we figure this out. Now, to make sure we understand this, I'm going to repeat the same question, but I'm going to change the exponent to something even. It doesn't matter 4 or 40. So I get to this one, but the exponent for instead of 3 is 4. So e to the power of 5 over 0 from left to the power of 4. 4 is an even number, just like that. This is 0 from the right as a result. And therefore, positive over positive is positive infinity. So that's why I want you to look at both questions side by side and see how we justify the answer. Okay? Infinity or negative infinity. The limit of x squared minus 2x over x squared minus 4x plus 4 as x approaches 2 from the left. If you plug in, you get 0 over 0, everybody. I'll leave it for you to verify that. But in general, when you have a rational expression, it's really a good practice to factor if you can. And that is really the technique. So obviously the numerator is very easy. You have to take out the common factor of x. But what is the denominator? I'm going to remind you of a perfect square trinomial. A squared minus 2ab plus b squared is a minus b squared. A squared plus 2ab plus b squared is a plus b squared. I hope everybody remembers that. If you look at the denominator, is a perfect square of x. So this is a perfect square of x. This is a perfect square of 2. And this, how do you get that? This one times this times -2. So you need a negative here. So therefore, becomes -2 squared. That's what we have here. Okay. This x minus 2 cancels out this exponent. Just erase my work. And we get the limit of x over x minus 2 as x approaches 2 from the left. So now if you plug in, you get 2 over 0. But now it is up to you to figure out the 0 from the left or right. So 2 from the left, like for example 1 or 1.9, minus 2 is negative 0.1. And that means the 2 over 0 that you get, everybody, now it's really 2 over 0 from the left. So this is really 2 over 0 from the left. And positive over negative is negative. And the final answer is negative infinity.